everyone. Can you hear me okay? I noticed the other speaker wasn't really using the mic, but I'll try to use both. Thank you so much for taking the time. My name is Gideon Mendels, not Michael's, but I'll work with that as well. And I'm the CEO and co-founder of Comet. And I'm really excited to be here today. My focus for today's talk is around machine learning system design for continuous experimentation. So just really high-level background about myself. So there's a couple more people joining. I started my career as a software engineer about 15, 16 years ago, and I shifted to working on machine learning and AI about 9 years ago or so. First as a grad student in Columbia, after that then another NLP startup, and my last position before starting Comet, I was working on hate speech detection and making comments at Google. And a lot of the things we've learned there definitely got into what we do today. And, for some, I'm sure a lot of you went through the same path, some coming from the software engineering background, where we have this amazing stack, right? Like databases, testing, monitoring, version control, deployment. We got methodologies, agile, Scrum, all of that. And then you join a machine learning team and someone emails you a Jupyter notebook. So that's really what got us to start working on Comet. I'll spend one slide about Comet and then we'll get to the meat of the talk. So for those of you who are not aware of us, we provide a machine learning platform. We essentially allow ML and data science team to help them manage the entire workflow of building models. So all the way from managing and tracking their data sets, code, experiments, parameters, metrics, being able to compare different experiments and understanding why one model is better than the other. All the way to the point where these models hopefully make it to production, and then we help them monitor them and understand how they're behaving there. We support some of the best machine learning teams in the world, Uber, Etsy, Ancestry, Affirm, and many more. And we have a booth right here, so if you want to learn more about us, rather specifically about my talk, you're welcome to come by and have a conversation and check out a demo. So for today, I just want to fix this. Sorry about that. So my focus today, I want to talk a little bit about the state of the machine learning industry with a specific focus on models in production and how is that relevant to this concept of continuous experimentation. The way I like talking about these topics, I know there's a lot of high-level conversations, and a lot of that starts sounding very similar after a while. But the way I like to present these things is by talking about very specific case studies from companies out there actually doing machine learning production. So that's what we'll do today. And at the end of the talk, we'll try to tie everything together. So. When we started the company about 5 years ago, the first thing we did before we wrote a single line of code is we interviewed about 250 data scientists and machine learning practitioners. And when we asked them about what are some of their biggest challenges, what are their biggest pain points, it was mostly around building better models, or models that are good enough, really. So at the time, the way we addressed that is by building our experimentation management solution. We were the first experiment management solution in the industry. But we've been doing this for over 5 years now, and in the last, let's say 18 months or so, a lot of our customers are starting to face new challenges, specifically around production. And production is not necessarily a completely new concept, right? We have some customers doing it for over a decade, sorry, something up here. So even though it's not a new concept, we often see these diagrams, video posts, and it looks like a solved problem. Oh, okay, we'll just go through all these steps and come back to it, and this is how you do MLOps or machine learning production. But the reality is it's far from being a solved problem. And I'll show you a few examples specifically about why is that the case. So, today, again, focus on what are some of the challenges. I'll try to talk about solution as well, so hopefully you can come out with some insights from this talk. And what are some of the takeaways that you can take from that when you're thinking about your machine learning strategy, machine learning ops strategy, and how are you kind of building something that's future-proof. So starting from the high level, how do you even know you have an issue in production, right? If you're working on a supervised task, typically your labels are not always available. If If you had labels all the time, immediately you probably don't need a model, which is, by the way, the best solution for everything if you can do it with, simple code. Sometimes you get the labels late, and that's helpful, but typically you don't have them right away. So how do you know when the model got something wrong? Additionally, if you're trying to approach it from a drift perspective, that is far from being a trivial problem. When you're thinking about drift, there's so many questions about which periods are we comparing, how long these periods are, and in some data modalities like text and images, it's essentially an undefined concept of how do you actually measure that drift. And additionally, there's just many ways for your models to fail. You could have like abrupt failures, which in some ways are like the easiest to detect and fix. So a data engineer changes something about the schema, the pipeline, your model, instead of getting 50 features is now getting 49, throws an exception, that's an abrupt change. But you also have these gradual changes where your performance of the model starts to degrade over time, and we'll definitely spend more time on that later. But I think the most important thing that, at least from earlier conversations, most people miss at first sight is your models won't fail uniformly. Typically, challenges in production happen in a subset or a segment of the data. So if your model is predicting a customer information or user information, you'll typically only see these issues in a subset of that. And more importantly, like some of these segments are way more important than others. So when you think about prioritizing, fixing them, prioritizing optimization of the model, that is definitely something to take into account. But I promised you I'll talk about specific case studies. So I wanted to start with something like super simple, like a really straightforward machine learning production example. So I picked Tesla self-driving cars. Hopefully you know I'm joking, and this is by far one of the hardest production environments and one of the hardest modeling tasks out there. And for those who are not aware, Tesla is trying to build autopilot and trying to reach what's called level 5, so essentially a completely autonomous vehicle. And one of the reasons this is so hard, this is hard in many ways. This is an extremely challenging computer vision task. Serving and inference on the car, really, really hard. But the hardest thing about this is if your model fails here, it literally could have catastrophic effects, right? And Tesla's approach to try to get to this point while taking into account that they can't make those mistakes is, I think, very, very interesting and unique. And it doesn't only apply for self-driving cars. So what Tesla noticed super early on is models that did really well in training would still run into issues in production. So that's what typically is discussed as production training skew. And unfortunately, it's not always something you can completely avoid. Their specific, or the biggest challenges they have is with these edge cases or out of distribution samples, right? Now, this touches on the larger topic of machine learning generalization. I'll not try to solve that in the next 15 minutes, but for those who are not aware, that essentially talks about how well your model performs the data it hasn't seen before. And generally speaking, there's some ways to try to evaluate edge case performance during offline training. At the end of the day, these are mostly research topics and eventually approximations. Now, when you think about out-of-distribution samples, we're talking about in the context of production, but they also create challenges when you're doing offline evaluation. Like I mentioned before, your model might perform really well in aggregate. Let's say you're using accuracy as a metric, you're at 95% accuracy, that's great. But you might have a subset or a segment of the data that the accuracy is 2% even, right? Depending how big that segment is. And offline methods are eventually fundamentally limited by the fact that they rely only on historical data. And at the end of the day, and this is, I think, the most important thing that sometimes data scientists neglect is that the only thing that matters is production. Because it doesn't matter how exciting your architecture is, it doesn't matter how well your model does in offline evaluation. At the end of the day, what we care about is how well it's doing out there in production. And of course, production could mean a million things, but the idea is how does a model perform for the case it was built for. So, the approach Tesla took to try to solve this out-of-distribution problem is what they call shadow models approach. So this is, I think, really fascinating. So what they're doing is they're training multiple models, just slightly different architecture, slightly different hyperparameters, maybe slightly different data sets. They're deploying all of them to the car. So let's assume you have 10 models in the car. Only one of these models is actually hooked to like the car and making the decisions and acceleration, stopping, and so on. The other 9 models are still making predictions in real time and essentially logging these predictions to some sort of database. And what they're doing next is they're using essentially heuristics and what they call weak labels to try to tag potential mistakes. So if I'm driving a Tesla, which I don't own, but if I'm driving a Tesla and the 9 of the 10 models say accelerate, but then I hit the brakes, that is a potential mistake, and it's weak as a weak signal, so it's not necessarily saying there's a mistake there, but it's tagged that way. And eventually they can build this data set with essentially these weak labels. They take it back to their extremely robust data pipeline. So they clean it up, they go through manual human annotation, they make these weak labels into strong labels, and eventually they have a new form data set. So what happens next, right? I'm guessing a lot of you expect, oh, that's easy, let's just retrain the model, put it in the car, and keep going. And yes, retraining is definitely needed in this case, but it's actually far from being a trivial problem, and this would be the first example of that. So essentially what we have here is this balancing act, right? So we have these small samples because they're used to be out of distribution, so we can make the assumption that their proportion within the larger data set is fairly small. And if we just retrain with that without boosting them at all, the model will likely not learn these specific samples. Now, if we boost them too much, we might encounter what's called catastrophic forgetting, where suddenly our models can drive roundabouts but doesn't know how to drive freeways. So you have this balancing act where essentially the model or the practitioner need to decide these specific weights for boosting. And this is an example of how your offline experimentation is never over. You never put them all into production and set up a retraining loop and let it run forever. You always have to go back and tune things. My next example, which I think a lot of people are aware of in production challenges, is drift, right? So Tesla was more of a production training SKU, but drift is also something you might encounter. And there's multiple types of variations of drifts, right? As you can see here, it could be completely sudden, it could be gradual, you could have blips. And I think what's interesting is, I think every one of these issues actually require a completely different solution. And we'll walk through one of these use cases, right? So this is from Bumble, the dating app. And essentially what the team built there is a model for user verification. So judging by the audience, I'm guessing it's been a while since anyone been in a dating app, but I'm not trying to insult anyone. But essentially what they're doing is the user uploads photos to the profile and then takes a selfie. And they're trying to match the person in the selfie to the person in the profile picture. If it's a match, it's a confirmed user and they can use the app. And if it's not a match, it goes into manual moderation. Right? They have a decent sized data set, millions of images, and they're essentially trying to minimize the number of fraudulent accounts. So, Bumble put this model in production, and it worked really, really well until it didn't, right? So, as you can see, at some point after a few months, performance starts to drop, in this case with about 10% decrease in model accuracy. Now, just to give you a sense, what is 10% in this scenario? So, 10% means about 10,000 manually moderation tests. That means that 10,000 profiles have to go through manual moderation. That is a team of people. It can't be scaled like AWS infrastructure, unfortunately. So that means there's a huge backlog of profiles that can't use the app. They can't use the app. They can't be monetized. Direct impact on the company, right? And what happened here, and again, this is sorry, the speaker notes here set up is a little weird. So the typical approach, again, if you see that type of drift, is to collect more data, retrain the model, put it in production. That's exactly what the team did. But unfortunately, almost no impact on the result, right? So I can tell you it took them quite a few cycles to figure it out. I don't know if anyone had any guesses of what might be going on, because we have a model, we got more data, we're retraining it, but it's still not improving. I definitely took me a little bit to figure out what's going on here. But what happened is, during the month 3 of model degradation, Apple launches a new iPhone. The new iPhone has a new camera, and as usual, the new camera is better, higher resolution. So they were retraining with these new images, but because of the high resolution, the model architecture wasn't actually able to capture it. So they tried a few things with downsampling, a bunch of tricks. Eventually what they did, they went back to experimentation, tried different architectures, found the model architecture that had additional few layers that fixed that and put that in production. So again, I think the story here is that you always have to go back to offline experimentation, and there's always additional work that needs to go in there. I think we covered this one. All right, the last case study for today is from Slack. So what we're seeing here is the model aggregate accuracy or result performance. And you see at some point a big customer decides not to renew and specifically complains about the model performance, right? Now, when we look at this as an aggregate, there's really nothing that kind of stands out or that looks to be wrong. And that is the issue with aggregate metrics, right? At the end of the day, like aggregate metrics, and I would say machine learning metrics in general, don't matter that much. The only thing that matters is the business KPI. Now, in most cases, the business KPI is not differentiable, so you can't optimize directly against it. But the way to get closer to it is by looking at specific segments of the data or breaking down your aggregate metrics to more granular. And if you look at that, you essentially see that the same model performance specifically on this customer is actually significantly degraded. So segments allow you to get much closer to business KPI. You can try to tie them together. But second of all, it really helps you identify the root cause. So if I'm a practitioner and I look at this, I know which model to look at. I know which specific subsets of the data to test this with. So this saves hundreds of hours of trying to figure out where the issue is, because if I have this segmented analysis view, I can really point it out. And maybe one thing to mention, segmented analysis can also be used in offline evaluation, where you can break down your metrics to these specific segments and do a very similar exercise before the model even makes it to production. All right, so I think it's clear that there's definitely a commonality for all these case studies, even though they talk about very different challenges in production, right? At the end of the day, the solution to all these problems comes from looking at production monitoring and offline experimentation as very closely related tasks. And in fact, experimentation is part of production. You want to be able to compare what you're seeing in the production and to compare that to the experiments you've done before. And the closer you can get these things together, the better your machine learning system will perform. And eventually, the better your machine learning team will perform. In fact, at Comet, we think this artificial split between offline and online is wrong. It's all part of the same iterative loop. So at this point, you might be asking yourself, okay, that sounds reasonable. I think that Gideon has a point here, but how do I actually get these things to work together, right? And one of the key here is you do this by adopting a model of modular MLOps design, right? So when I talk about modularity, I'm really talking about instead of trying to adopt like a completely end-to-end, one-size-fits-all solution, is to take a more best-of-breeds approach. The main reason is modularity is super crucial for these ML teams, and it really protects your ability to continue to being agile in the future and maintain this flexibility for future changes. We talked a little bit about some of the changes we've seen so far, but when you think even something as simple as training models, 4 or 5 years ago, everyone were training their models from scratch. These days, it's much more common to take, a pre-trained model and fine-tune it. So these things are moving very quickly. The term MLOps did not exist 5 years ago when we started the company, and they will continue to move as fast. And really, as practitioners, as people operating in this industry, we have no ability to foresee all these changes. So the only way when you think about your strategy is to pick a modular approach that allows you to remove certain pieces, include exclude certain pieces, build some of these things in-house, bring best-of-breed vendors for others, and so on. So again, just to wrap this up, the best performing teams I've seen by far are those who pick the modular approach. Even companies like Uber, who built Michelangelo, which is considered, I think, the first MLOps platform out there, and they started, I think, 6 or 7 years ago, came to us about years ago and said, hey, like, there's some areas we have to focus on as teams, specifically in our case, the serving component is extremely complicated. But there's some areas where we'd rather work with vendors and go much, much cheaper. So even then, we have an entire platform in place, which I know a lot of organizations are aspiring to get to, are moving to a more modular approach. So just to wrap up, a modular approach will prioritize this flexibility and customization, will allow you and your team to incorporate new tools, new libraries, new models, stay up to date with the industry, and essentially allow you to shift strategy, not general engineering strategy, but how you approach these problems, and how you keep with the latest research and the latest tooling out there. So I think that's all I have for today. Thank you so much. I'm happy to take any questions now. Please go ahead.
So how about the modular approach? So you have software like H2 or some other things and
Yeah, so I think, so for those of you who didn't hear, the question is like, if you're using something like H2O AI, how can you be modular? And I think the answer is within the question. I think, as far as I understand, H2O has an amazing product, but it's completely end-to-end, right? So if you're buying into a vendor, or even if it's something you're building in-house that's completely end-to-end, it is hard to be modular. So the approach is potentially using H2O or other tools to specific things, and then build the best-of-breed solution. Yes.
So so there's supposed to like modular. So you need to like come to one architecture to modularize the.
So yes and no. There's a lot of blueprints out there, but yes, at the end of the day, it depends on your use case, right? So that's the thing here. There isn't one size fits all. Otherwise, the vendors would solve it for you. So depending what type of model you're working on, are you doing online predictions, offline predictions? So there isn't really. There's a lot of commonalities between them. And I can, if you talk to me later, happy to share some of these blueprints. But again, the good and the bad news is there isn't a one size fits all.
When it comes to smaller companies, it's relatively easier to be down using this platform, but when you're looking at bigger companies, most of my customers, challenges, particularly in my opinion, like the people landscape is relatively cross environment. And you would feel confident to live in advising on-prem cloud. In such case, what is your big point for building a scalable
So I think especially companies, bigger enterprise that have complex environments, multi-cloud, hybrids, VPC, on-prem, all of these things together, is exactly why you want a modular approach. To have that type of flexibility, an end-to-end platform that tries to do everything is rarely be able to adapt. And this is, we're not talking about user requirements, but really infrastructure requirements. Those would rarely be able to adapt to that. So hopefully, I think, did I answer your questions?